I'll go off and grab.
Yeah, people are wondering.
I think I'll just stop.
Okay. Looks like there's people still coming in though, so.
So, good afternoon, everyone. So this is our fourth lecture today. So I'm going to have Professor Manfra here. Let's welcome him. So he's going to talk about, continue yesterday's lecture, talking about braiding, anyonic braiding, experimenting.
Okay, great. As mentioned, I'm going to try to go into a little bit more detail today describing how we can design our devices, control their parameters, and use that to extract information about the anyons in the system and how we can be quantitative about it and put a little bit more detail on some of the things I presented yesterday, and then move from 1/3 to more complex states. The primary one we've worked on so far is 2/5, one of the daughter states of 1/3. But of course, I'll have to break quickly and say I too thoroughly enjoy and recommend Modern Condensed Matter Physics by Kun Yang and Steve Gervin. Everyone should use it in their classes. I do have a little disclaimer though, I'm being sponsored and compensated by Kun Yang.
Just like the measurement.
I'm not going to show you. The sales of this book is not enough to do that.
But nonetheless, in all seriousness, it is a very nice book, and so just give a plug since he was our last speaker. All right, so let's move on. Towards the end of yesterday's lecture, I was saying how we could develop devices in which the standard periodicity of the AB oscillations is interrupted by these phase slips. And this was the first data. And what we did is analyze the evolution in between the phase slips is just the normal AB evolution. And then these phase slips are associated with the introduction or removal of a quasi-particle. And remember, from the expression, the simplified expression, that the interference phase is the sum of two terms, the AB phase, where it's been scaled appropriately by the effective charge, and then this term here, which is sensitive to the number and statistical angle of the anyons. So we fit the conductance between the jumps to get the value of the phase jump across. When we did that analysis, we got a value of delta theta over 2 pi very close to 1/3, as expected from theory. And this was evidence of the detection of anyons in our interferometer. Okay, so as I said, the theoretical prediction, when you have no bulk edge interaction and you can minimize all the other competing terms, is that the statistical angle is 2 pi over 3. We measure something very close to that value in the experiment, suggesting that we had mitigated some of the complicating factors, including bulk edge coupling, this large charging energy, and had maintained high edge state velocity to have good coherence. So let's go into that in a little bit more detail. I drew those lines just by hand. I said, well, if you look at these slanting lines, that's where the phase slips occur. And there's a question of, well, what do you know about those? Well, the slope of the discrete phase slips is something that we can actually extract and know from our device parameters. So these lines, if you just go ahead and calculate them, use your ruler, you get a slope about half an MeV per millitesla. And remember that these phase slips occur when a quasi-particle enters or leaves, such that the electrostatic energy that it would take to stay at perfectly 1/3 filling exceeds this quasi-particle energy. There's a competition, and so the system defaults to actually, in these particular cases, keeping the charge on the interferometer constant. That's this delta Q net term. And delta Q net can be written as a sum of terms. It looks messy, but it's really not. This is just the charge contained in the condensate. That's because it's a 1/3 filling, you know exactly what the charge is. If there are any localized quasi-particles, it's augmented by that charge. And of course, overall charge neutrality is maintained. So there's the background charge due to the ionized dopants and that give rise to the electrons in the first place. And any additional charge, because we have gates, we can induce charge using those gates. And that is related by an alpha term, which is the lever arm. When we modulate a gate potential, what the effect does that actually have on the charge in the quantum well? And the thing here is, while we've just drawn the slope by hand, we can actually predict what it's going to be using known, well, not known, but extracted parameters from our device. So we know what the total lever arm, if we go to B equals 0, we look at Coulomb block, we make it a quantum dot, we look at the spacing in Coulomb blockade, and we can extract the lever arm from that. That's the lever arm for changing charge both in the bulk and on the edge. There's no distinction at B equals 0, so it's a total charge. Now we can go into the integer regime and use the side gate plungers to basically learn how much we're changing charge in the edge states. And that is a parameter that we can extract knowing the area and the voltage, periodicity in gate voltage. And so knowing those two, we can actually extract out what the coupling is to the charge in the bulk when we're in the incompressible regime. It's just the bulk term is the total lever arm minus the lever arm just to the edge, and that comes out to a specific value about 0.07 inverse millivolts for our system. So when we do that, of course, if we have constant net charge, the derivative, we can set the derivative equal to 0. That gives the following relationship that dg by dv has to be equal to a certain set of quantities here. The filling factor is known, the area is known. That's the fundamental flux quantum. And this alpha, which is the lever arm, I've just told you we've measured. You do so, and you get an answer about 0.44 MeV per millitesla. So there's good agreement between the observed slope, that's just the dashed lines, and the slope predicted based on our known device parameters that we've extracted through the differing tools that are available to us to know these couplings. So there were some questions later about spacing and slopes and where things occur. And I just wanted to emphasize this point that while the spacing, where in this plane those isolated quasi-particle states reside is not under my control. That's set by the disorder potential. Once that is fixed, the other parameters of how I couple to those via magnetic field, gate voltage, all those sorts of things, is something that I can understand and extract, and then make comparisons between my measurements and what theory would tell me they should be. Okay. So also in a question about reproducibility, these are not, there's many reasons why these are not just noise or charge fluctuations. But one thing is that the position and value of these phase slips are fixed, meaning I can do, there isn't hysteresis or time dependence. I take a scan. To take this scan probably took, in the old days, something like 2 hours. Then I do another scan over the same region after it, and there's a couple hours interval, and the patterns are more or less exactly the same. So this is not noise. This is set by the mesoscopic disorder configuration in my device. And in both cases, you can do the analysis, and the anyonic phase angle again comes out to be 2 pi over 3. So the effect is robust and understandable in terms of real device parameters. Okay, now I also said it was very important that we be in this incompressible regime that's around the center of the plateau, where the system favors keeping fixed filling factor that may add charge, as opposed to just with each flux quantum insertion adding quasi-particles. But that's only sustained for so long. You can only do that for so long when it eventually becomes energetic along the center of the plateau, before it becomes energetically favorable to start rapidly introducing quasi-particles with flux insertion, as you might expect. And then this theory, that model that was worked out by Rosenau and Stern in 2020, after our initial 2019 results, oh boy, put some numerical numbers that we could compare to our experiment. So there's a competition between the energy to create a quasi-particle and the electrostatic energy cost to just add charge to keep you fixed. And there is a transition. If we say the center of the plateau is B naught, that's the center, there's going to be some D critical where the system switches over. So instead of having the periodicity of 3 phi naught in the incompressible region, because that's scaled by the effective charge, there will be a transition point where the periodicity goes over to phi naught and quasi-particles are added upon flux insertion. Okay, so just as an experimentalist, we think of the central region as the place where the chemical potential is in a region of very low density of states. If I go to the lower magnetic field, the chemical potential is in a position where there are states available, quasi-particle states. And of course, if I go to higher field, I can induce quasi-holes, and I would have a similar symmetric looking condition. So this width that I talked about of how wide we have a region of 3 phi naught oscillations is calculated in this paper. It depends on the gap, the excitation gap in the bulk, the filling factor, the effective charge, and what you might call the charging energy, the capacitance of the island that we've created in the interferometer, which of course that is under our control by design. So you put those numbers in, and what you get, we measured the excitation gap. You should get a region approximately, by this calculation, about 530 millitesla wide. Then we expanded the range over which we looked for interference. The central region, now it's compressed, but this is the central region, incompressible region. And then we had this very dramatic change in interference where we lose magnetic field dependence and the oscillation amplitude goes rapidly down, meaning the signal is just much smaller. It looks like a large phasing. And we asked the question, well, Rosenauer and Stern would say we should have this transition, but can we explain the data we see given the parameters of this device? And the answer is yes, because if we change the flux by phi naught in the compressible region, there'll be an evolution of the AV phase of 2 pi over 3, which is a continuous, that's just the evolution of the phase as you insert magnetic field flux. but any abrupt change coming about from the addition of an anion is discrete and minus 2 pi over 3. So on average, there's zero change in phase. There'll be some evolution, and then you should see an additional little schnick in the data. But given the temperature we were at and the energy scale for thermal smearing, which we can calculate to be about 4 millikelvin, which was actually below our fridge temperature, what we believe we saw was a thermally average signal where these lines of constant phase flatten out and weaken, but we don't see any additional structure because we had overcooked it by making the device so have such low charging energy that the temperature scale became exceedingly small. Okay, so we looked at the thermal dephasing in the incompressible region and then in the flanks, and we saw consistent with a exponential function, we could extract an energy scale that in the compressible regions was approximately 30 millikelvin, but in the incompressible region was closer to 100 millikelvin. So the amplitude of the oscillation is preserved. There's less decoherence in the incompressible region for those AB oscillations. There's more decoherence as measured by this extracted temperature scale in the compressible regions where the density of states is higher and the quasi-particle number can fluctuate. Okay, so the large gap protects interference in the incompressible regime and certainly hurts the fluctuations in the quasi-particle number, certainly hurt the interference coherence in the compressible regime. So this has been studied theoretically by Park, Yuval-Jeff, and Sim. So we have a thermally smeared population in the compressible regions giving rise to the signal we see. Okay, and this is consistent with very simple modeling where you assume that you have an energy scale associated with the gap and keeping the charge fixed, and you assume effective electron ratio between the temperature and this energy scale, and you would start out with something looking like this at t near t equals 0, the 3 phi naught periodicity, where you see this sort of sawtooth pattern. But as you get warmer and warmer, that starts to fade out. So by the time you get to a realistic temperature scale, it looks much more like the data we see. Okay, and so this was all consistent with what we saw in our first, the experiment of 2020. So this taught us a valuable lesson. So if all of this is true and we're getting hints that we actually have control over device parameters and therefore those device parameters affect what we see and tell us about the presence of anyons, we should just, we have a hammer, let's keep beating on that nail. So what we did is now we first went to the regime where I have the parallel plate capacitor and I've really effects by making that capacitance large. Now what I'm going to do is I'm going to throttle back a little bit, make the device smaller, also change the 2-deck density a little bit lower so that I can actually see the effects of bulk edge coupling. And that makes certain things more visible, and it's also a way to test the theory against what we see, because there are predictions about the impact of bulk edge coupling, quantitative predictions, and so it's a way to see if we can really make sense of a larger collection of data, not just looking at individual phase splits. So what we did is we made a device now that's 800 nanometers by 800 nanometers. The density is reduced slightly to about 6 times 10 to the 10, and we're going to explore what happens here, and hopefully this will convince you that we have pretty good control and understanding of what's going on at 1/3. So in this device, it's the same type of device, it's just smaller, and now we're working in a range of magnetic field. Here's the 1/3 plateau in the bulk measured right next door to the interferometer. We're down around 7 to 7.5 Tesla. So the interferometer is twice smaller in area. And we see negatively sloped AB oscillations near the center of the plateau. with periodicity 3 phi naught as expected. But we see something else that's pretty interesting. We have sustained amplitude out in the compressible regions where there's a transition from the flux periodicity of approximately 83 millitesla. Out in the wings, it changes to approximately 21 millitesla. And we can see the preservation of amplitude and periodic structure on top of those completely washed out lines. So this data, as I'll try to show you, is consistent with anyonic phase slips in the incompressible region and in the compressible regions at high and low field, the presence of anyonic braiding with a compressible bulk. So if I zoom in to show you the level of resolution we now have, you can see that the phase slips in the incompressible region are very sharp. AB evolution, slip, AB evolution. You can see them very crispally. But then as we transition into the incompressible region here at higher field above, say 5.5 Tesla, you see the lines are flat as they were in the larger, earlier device, but they look like they're breathing a bit. There's modulation on it. And plus, some of the amplitude is preserved. It's not so far as much suppressed as it had been previously. So this data allows us to say that we're actually understanding what to do and how to modify designs in order to probe physics. So again, this is reproducible. There's no real dwell on this. It's just showing that over many hours, these things are all in the same place and give the same values. But let's really take a hard look at operation in the incompressible and compressible regimes. Again, just to emphasize, twice smaller device. Modulations are clearly visible now in the high field here and low field region with a period of phi naught. And the incompressible region I'm defining is basically this yellow band within the center of the bulk plateau. And then my excursions are on either side of that. So if I look at the periodicity, it's 3 phi naught in this region and phi naught out in the wings. How do I know it's phi naught? Well, I can just say it's approximately 3 less. But I can also do a little bit more. I'm going to be able to make calculations based on the parameters of my device. Remember I said yesterday that I depend on knowing these parameters, KIL, which parameterizes the bulk edge coupling, KI, which is essentially the edge stiffness determined by the velocity, and basically those are the most important ones. Now, that simple expression for the anyonic phase development that I told you about earlier gets modified in the presence of bulk edge coupling. Now, it may look complicated and scary, but it's really not. It's just being that there's this extra term in the middle that accounts for these finite couplings from the bulk and the edge, and the edge mode stiffness. Okay, there's still the original term from AB, and there's the term due to the anyonic phase contribution. The anyonic phase contribution, of course, is fixed. That's set in theory, but what you actually see in this interference phase gets modulated by the fact that we have this finite coupling. And all these parameters in here are things that I can extract from my device. And I'm going to try to do that and determine the consequences. So what we're really trying to do, and I'm not going to go too deep into the theory, it's Burt's paper with Stern and Nader and Rosenauer, that can account for the presence of bulk edge coupling. The area, as I mentioned yesterday, can change due to the Coulomb interaction. Rather than thinking of it as this very inert object, there is a little bit of breathing that goes on when you have finite coupling. That gives rise to a simple electrostatic energy function where these are just essentially saying what the energy to add charge to the edge, how much it costs because of this bulk edge coupling when you change the charge on the edge and in the interior, and then this interior term as well. Ki is the edge stiffness, Kl is the interaction of localized quasi-particles with each other. Not a big deal in our case in that when they're very dilute, KIL parameters are, this is the bulk edge coupling. So then you get, as I said, this big equation for the interference phase, but it is written in terms of parameters we can extract. So we do that first. We can get the ratio of KIL to KI by looking at nu equals 1, where we have just electrons, and looking at the compressible versus the incompressible regime. So if I take a wide swath of magnetic field at nu equals 1, even though I have electrons, this breathing can still happen because of the bulk edge coupling. And in the incompressible state, of course, there's a very large gap at nu equals 1. The system is not prone to creating quasi-particles. It stays fixed. At fixed filling, you have a periodicity of about 28 millitesla, but in the flanks, again, about 21 millitesla. And from that, you can just write an expression for what delta V central is in terms of these parameters, KIL, KI. And if you do this, you can see that the change from the central region to the outer ones results in a ratio of about 0.25. Now, 0.25 is moderate bulk edge coupling. It's not super high. Super high is above 0.5, half. That's when you transition into this Coulomb-dominated regime. But by just looking at the ratio of periodicities, I can extract out what this coupling is, and the value is close to what we actually measure directly from finite bias. So there's a multitude of ways of extracting KIL and KI. If we just look at the Fourier transforms, you can see that there's a definite shift in the high and low field regions relative to the center or incompressible region. So, okay, you can insert that, and I'll come back to it. That gives me something just from looking at the ratio of the periodicities that tells me about bulk edge coupling. Let's say I want to be a little bit more microscopic about this and say, how can I extract that from directly from the device? Well, you can estimate the couplings, the constants, by breaking the energy of the system into an interacting part, the interaction, the bulk edge interaction, and a single particle, which is basically looking at the dispersion along the edge. And if you do that, you can write out forms for this interaction term and the single particle energy, and you can estimate those from measurements of your devices. So we estimate E internal from the B equals 0 Coulomb diamonds. That spacing in the diamonds, sorry, it's down here, tells you about this 2 times E squared over C, which is the capacitance. So we can measure this directly. Okay, so that's related to the internal energy by this equation. And we can estimate the single particle energy from finite bias edge velocity measurements. Remember I said that if we not just work at 0 bias, but put a finite bias, basically add an energy, inject energy into the system, then we can look at the periodicity of that structure, the resulting structure, and the conductance measurements to extract out basically, in some ways, the dispersion and what the velocity is for the edge modes. Okay, so if I look here, these color plots here, now what we're looking at is the change in conductance, but I'm looking at an AC wiggle that I measure, but I'm also applying a DC bias to inject energy. And I can measure that as a function of the gate parameters of the interferometer. And by looking at the nodal structure, these spacings where there's a transition from red to blue, that spacing is related to the edge velocity, very simply. And so I can extract these parameters from more microscopic quantities of the device and extract out my own KIL to KI ratio, and it's approximately 0.31. Pretty close to the value extracted in a completely different way at nu equals 1 from the interference patterns. Okay, this is the interference at nu equals 1. So what the point of all this is to say that we actually have handles on fairly microscopic parameters of our device, and therefore can then say how they impact the expression of anyonic braiding statistics. Okay, so the key parameters for AB versus Coulomb dominated are KIL and KI. We get them, these values, from a combination of Coulomb blockade, differential conductance measurements, and when we put all that together, we again come up with this parameter that's much less, not zero, but much less than 0.5, consistent with the AB oscillations you see. Now, the crucial part, well, maybe I'll come back to this, but the crucial part is, oops. Well, why don't I do it? I'll do it here. So let me show you a very clear manifestation of how these coupling parameters really affect real devices. So if I go to nu equals 3, now I'm not worried about anyons at the moment, this is an integer quantum Hall state, but it has 3 charge modes, right? There's 3 len, there's a 2 from 1 lambda, well, n equals 1 spin band, okay? So if I look at the interference where I'm here on the conductance curve, you ask about how I control the backscattering, several people did. I can look at the conductance of one of these QPCs and see it's fully quantized, which means I'm transmitting all 3 modes. And I keep squeezing on the QPC until the conductance actually goes below 3 e squared over h, right? I'm weakly backscattering now that innermost mode. So if I sit here and then operate the interferometer, under those conditions, the interference pattern looks like this. Well, that's the wrong way, right? That is not AB behavior. That's indicative of Coulomb-dominated behavior. Okay, well, you have 3 modes. They don't all reside in the same position in space, and therefore they don't all see the same gradient in the electric field, and therefore they don't all have the same velocity. The inner modes move much more slowly. So if we do the analysis that I talked about before and extract this KIL over KI, for the innermost mode is 1/3, at 3, just the innermost mode, is 0.62, consistent with Coulomb domination of the interference pattern, meaning I've crossed the threshold to be from AB to CD, and the parameters, the more microscopic parameters of my device, agree with this. Now, I can also change the conductance. I can say, well, okay, I'm scattering, just weakly backscattering the innermost mode, but then I come down, and if I go to the second plateau, that's 2 modes fully transmitted. The first innermost completely backscattered, so it's just circulating within the interferometer. And then I go to a regime where I'm weakly backscattering the middle mode, just the one in the middle. And then I look at the interference, and what you're going to see is it completely flipped. So nothing's changed other than the conductance of my QPCs. So I'm backscattering different individual modes. And now the lines of constant phase have the negative slope, as you expect from AB. Note that there's these oscillations on it. Remember, the theoretical prediction from Halperin et al. Is that depending on the coupling, you can go from pure CD, straight lines with positive slope, to pure AB as you tune the relative level of Coulomb coupling. In this particular case, we're able to actually extract, again, these parameters, the KIL and KI, and lo and behold, it comes out below 0.5, suggested, not 0, but we're in the AB regime. We're in AB, but with strong enough Coulomb coupling that you see the modulations along the length. Now, I can go to the extreme, way down here on the conductance curve, where I've completely backscattered both the inner, middle, and now I'm just partially transmitting the outermost mode. And something very interesting happens. It stays AB, it's even more AB, and then there's a period doubling. That's some details of physics. It's probably too much to go into here, but we can see that it stays with AB, and there's some interesting effects. So the point of showing you this and is to say we really do have control over our device, and I can tell you where it's operating, meaning I know about the microscopics, at least at this level, to say if I'm A, B, C, D, which one is a fast-moving mode, which one's a slower-moving mode, etc. So that's really important. Now, you want a question?
Yes, so I was just questioning, why is the magnetic field different for these three edge states? The x-axis in these three.
Oh, they're slightly different. I don't know how the labeling's going, but there's, the incompressible region for 3 also is fairly broad. So, no, they're not labeled properly.
So they're all in the incompressible.
Yeah. It's not be switched, and there are slight. I could put them on a consistent scale, but they're all in the same area.
So, on what parameter tune it from the innermost to the outermost? Did you tune by the QPC or
Just the QPC?
Not on the test.
So the side gates here, these are called plungers, if you will, from quantum analogy to quantum dot. These plunger gates are fixed. And what I do is, with these QPCs, I can start pushing more negatively to start backscattering more and more. And I do that, and I eventually switch so that I'm completely backscattered the innermost mode. So the innermost mode doesn't go across the QPC, it's just circulating around inside. And then I'm fully transmitting the outermost mode and partially transmitting the middle mode. And so that coupling you see there is controlled by these two gates, the QPCs. And I have maps, and you can see where they are, so you know where you are, what you're doing. Okay, so you can, and this is why this level of control, the lack of hysteresis to be able to tune back and forth is important, and why becomes more of a, say, working at 5 halves, you have to have the same level of control to be able to say quantitatively about what you're doing. Okay, so just to show you that this Coulomb-Don behavior is consistent with the nonlinear differential conductance measurements, looking at the nodal structure, seeing that the spacing corresponds about to 45 micro EV. We can make these estimates, as I just said, and all the data is consistent, self-consistent, which is an important point, with being in the Coulomb-dominated regime for the inner mode. Okay, that's the ability to selectively backscatter or transmit multiple modes is important, not so much at 1/3 where there's just a single mode, chiral Leininger liquid, but when we go to 2/5 or 5 halves, you're going to have multiple edge modes, and you have to know exactly what you're backscattering and by how much you're backscattering it. Okay, so just to say, now I've parameterized my device, and you say, well, you have these really crisp phase slips. Are they still consistent with 2π/3 as the anyonic phase? Yes, but there's a little bit to it. If you actually look at the value of these phase slips, like I did before, the average value, now this is the phase, this is the interference phase, not the anyonic phase itself. The value is minus 0.24. Remember, it's supposed to be minus 0.33. Okay, and in the first device, it was minus 0.33 because we had so much quenching of the charging energy. But now they're nice and crisp and clear, but the value is a little bit off. But since I know what KIL to KI is, these parameters of my device, I can see how the interference angle is related to the pure anyonic phase angle through these coupling constants. Okay, and if I do that, the anyonic phase, I've measured everything here now, corrected for bulk edge coupling, comes out to exactly 1/3. So I don't know, for me as an experimentalist, this is really cool because it shows you can perturb away from a given condition and still understand and make quantitative sense of your device. And in fact, it's actually helpful. Okay, so the fact that we can tune the device parameters so that the interference phase represents the anyonic phase, but it's modified by bulk edge coupling is important. And again, all of this is consistent at 1/3. We're not at nu equals 3 anymore with the parameters extracted by looking at the differential conductance measurements. Okay. The phase analysis, we can do, FFTs of all this stuff. We do it 8 different ways. The value we always get is about 0.33 for the phase divided by 2 pi once we include the effects of bulk edge coupling. So hopefully at this stage, you have a better sense of that these devices are actually representing what I'm telling you they are, and they actually work in detail, both in the incompressible regime in the middle, but also out in the incompressible regime, where now I see it's flat, but I have constant AB evolution and then a back kick because of the introduction of a quasi-particle is discrete. So this behavior down here looks much more like the ideal sawtooth pattern that I told you. At least it has the right periodicity. It's flat on average, but there's 2 components: a small amount of AB evolution, continuous, and then a discontinuous jump with the introduction of a quasi-particle. So now, to make connection to the earlier data, let's look at the temperature dependence of the phi naught oscillations out in the flanks. So now I'm down at 10 millikelvin, and you saw the nice behavior I showed you before. Now we just increased the mixing chamber temperature to 50 and then 90 millikelvin. Now, this data starts looking a lot like the previous device data at low temperature. Now I've intentionally introduced thermal smearing by raising the temperature. And look, the intensity goes way down, it all gets washed out, and they're flat lines again. So I've traded bulk edge coupling for temperature in this case. And so this data at 90 millikelvin looks a lot like the data at 10 millikelvin from the larger device with more bulk edge coupling suppression than this one, okay? So again, we look at the compressible to incompressible to compressible region and transitions. And as I said, I'm sort of belaboring some points here. I can see the difference clearly. I can see the difference in the FFTs of the primary frequency. If I look at nu equals 1, that's black, those are phi naught oscillations. If I look at 1/3 out in the flanks, I have the same periodicity as I do at nu equals 1, phi naught. Then as I go at 1/3, but I go up in temperature, I have no signal. So again, self-consistency checks. Okay, so again, you can look here to here, and that looks like the old device going from 10 to 9 millikelvin. And yeah, you can do all sorts of FFTs and see where the central peaks are. If you have any questions about the details of this, please ask. We can go over it. And what I do want to emphasize is it's not just measuring interference. We have these basically tools from quantum dot spectroscopy that we can bring over. And doing finite bias measurements is really helpful. We can either do differential conductance, where we're monitoring a little AC wiggle, but we're imposing a DC offset, or we can look at direct DC current, and the patterns and zeros you find in these are representative of very important information: edge state velocity, Luttinger liquid behavior, whether the spacings are even or not, and all of this can really be connected to some of the early predictions going back to 97 by Shimon, Wen, Zombie, and Kivelson. So, you know, a lot of this stuff was already laid out back in 97. Halperin and, you know, finished out some of the messy details, okay? So it's all sort of self-consistent, and I think we have a pretty good idea that we have access to anyons, what the anionic phase is at 1/3, which was our primary goal. Now the real question is, okay, you've done this for abelian anyons in the simplest case, 1/3, there's one chiral mode, there's no complications. How applicable is this technique to more complex fractions? And the first most more complex fraction to look at after 1/3 is 2/5. And 2/5 is where we're going to extend our measurements, hopefully in the end of at some point at 5/2 as well. But I posed it as a question: can we extend our techniques to more complex fractions? And it's not immediately obvious. In fact, there's papers out in the literature by Dima Feldman and Halpern that talk about the robustness or lack thereof of robustness of quantum Hall interferometry. And what saved us in some way at 1/3 is one, the very large gap, and there's a single mode. If you have multiple modes and they're interacting and they're in soft confinement, you can have all sorts of physics going on at the edge that will confuse or make some certain observations very, very difficult. And so I want to say it's just we were able to do it at 2/5, but it's not obvious, and it was much harder. So 2/5 is interesting. Why? Because the fundamental smallest available charge is not the filling factor. It's 1/5 E. Okay, the filling factor is 2/5, but the charge of the lowest lying excitations is 1/5, and the phase angle is 2 pi times minus 2/5. So there's differences there that we should be able to expose if the technique is working well. As I say, we have a paper that's we're almost going to be published in PRX, but in which we're actually able to independently interfere the outer mode and the inner mode and measure a charge very close to 1/5 and the anionic phase after some fairly elaborate analysis that's essentially 2 pi over 2/5. Okay, and so for us this is really good news. It's very hard, and it's hard for well-known reasons, but it bodes well for the future. So let me tell you a little bit about that. So we again had to modify the header structure and device to operate at 2/5, but the key attribute is that we can independently interfere the inner and outer charge modes. So let me show you, the plot on the left is something called RD. You deplete the gates, the QPCs, the plunger gates, so you know transport has to take place through the interferometer. It's not going through the bulk. But you're not deplete or charging up the QPCs so much that you induce significant backscattering. If you do that, where we've just depleted everything, so the transport has to go through the interferometer, the black trace is RXY, your standard old RXY in the bulk. RD is the Hall voltage across the interferometer. And under these conditions, you have good quantization over finite ranges in field. Here's nu equals 1/3. There's an extended region where they overlap. So you have full quantization, meaning full transmission. Now at 2/5, the range is narrower. The range over which the RD is quantized is narrower in B field than the bulk plateau, but nonetheless, it comes down to 2/5. Now, if you look, 3/7 is well quantized in the bulk as well, but RD is not under these conditions. So there's already scattering in that case. But we start out from a position at 2/5 where we know we can fully transmit the edge states, and then we start inducing backscattering. So here's what an individual QPC trace looks like. So we start off with full 2/5 conductance, and then we start partially backscattering, and that's when we're partially backscattering the inner mode. If we keep depleting, we reach another plateau. That's the outer one, what you might call the 1/3 mode. It's quantized in units of 1/3 E squared over H. And that means we've fully backscattered the inner mode, and then we can start partially backscattering the outer mode. Now you'll notice things are a little bit more complicated here. We have these features, they're just resonances of the QPC, meaning that if you want, they're a junk effect. But these are reproducible, and we know exactly relative to inner mode and outer mode how much we're transmitting. Okay. In fact, the sharpness of the edge confining potential is central to doing this. This is not what you usually see. What you usually see is maybe you have some quantization around 2/5 and then just junk going down over a long magnetic field range, which is indicative of not sharp confining potentials and loss of resonance. Anyway, so this is our starting point. We know what, in some sense, as experimentalists, what we're doing. Okay. Now, we go to interference. We're going to start with the outer mode. So I'm fully backscattering the inner mode. That's more complicated. And we look at the pattern. Now, remember, the bulk is in 2/5. It's not 1/3, but we're looking at just the outer mode that actually is very similar to the single mode at nu equals 1/3. In fact, if I didn't tell you what filling fraction I'm at, you might say, oh, you're just looking at 1/3. The pattern is very similar, but this is at bulk filling factor 2/5, but where the inner mode is completely backscattered. And you see similar behavior. So the outer mode has a central region with incompressibility, negative slope at 2/5, very similar to 1/3. Some quasi-particles, the range over which this incompressibility exists, by the way, is consistent with the inner mode I'll get to in a second. You know, there is some quasi-particle creation. It's a little bit more complicated analysis because actually the localized quasi-particles are E/5 quasi-particles in the center. And then there's a little incompressible strip. There's different, you know, as you go out, there's compressible strips as you go towards the edge. The outer mode interference continues up to 1/3, but is greatly suppressed in amplitude when the bulk is conducting. So we can actually monitor this, just so you believe me that I'm at 2/5. I can monitor this all the way from 2/5. I go, here's the bulk transport below. I go into this highly compressible region. There's finite RXX, and the RXY has a slope to it. So this is conducting, and you see a loss of interference. And then as I come into the 1/3 state, it starts looking again like the previous data I showed you, okay? And so we can follow this particular outer mode. I mean, there's some adjustments of QPCs you have to make because the transmission changes a bit, but you can track it all the way from 2/5 to 1/3 and follow its evolution. So this, in some ways, is nice in that it confirms in some ways that the outer mode at 2/5 looks like the 1/3 mode. But if that were it, it'd be boring. That would be the end of the story. But as support data, it's very comforting. Now, if I go into the incompressible region, but now I'm only partially backscattering the inner mode, I see different behavior. And you might say, well, is this just junk? And the answer is no, it's actually what you expect. So remember, in the incompressible region, the tunneling takes place primarily at the QPCs. That's where the backscattering occurs. In a compressible region, if I have a bunch of quasi-particles and, you know, sort of the transport is activated, I can actually have transport to the bulk anywhere in the device. And out here in these compressible regions, that's what we seem to be seeing. That's not interference, it's just resonant tunneling. It's not indicative of an interference process. But in the incompressible region, we can actually analyze the patterns and hopefully convince you that what we're doing here is correct and indicative of anyonic phase for these E/5 quasi-particles. The thing to remember is at 2/5, the AB period is even longer. You know, the charge is smaller. So the evolution of AB phase in magnetic field is very gradual, very slow compared to 1/3 or before. And so the periodicity you'll see just the magnetic field is stretched out. On the other hand, the anyonic contribution is large. It's 4π/5, and so it is a large contribution to any evolution of phase, and that's what we'll see. So if we look along particular lines, look at the phase evolution, red, blue, along these lines, and compare it to what you see to vertical lines, you see very different behavior. So along these diagonal lines, red, blue, blue, you see sinusoidal behavior that is indicative of AB evolution. You say, well, how can the AB is tilted the wrong way? That's not the right way to look at it. The AB evolution is there. It's just the field scale over which we're looking is very small compared to, say, n equals 1 or 1/3. So the amount of evolution that you expect for change is rather small. Now, it's interrupted by phase slips, by discrete jumps in phase that occur across these dashed lines. And that large change in phase associated with the introduction of quasiparticles is what is the dominant term in the interference pattern. So you actually have to know the values of the coupling of your device to analyze it properly, and that's what we can do. And so when we can actually analyze these phase slips, and what we come out with is a phase slip. This is the measurement of the interference phase slip that averages around half times 2 pi. Now remember, I'm looking for 4/5 2 pi. Let me make sure I get this right. Half, and this should be closer to 2/5. Sorry, because of the extra factor of 2. But so I'm not quite there, but remember, this is the phase slip in the interference. I have to account for the bulk edge coupling, which I did in the previous example. So just to pick on this point a little bit more, remember the naive expectation without bulk edge coupling is the interference phase is related to the anyonic phase in a very simple manner. And the charge is supposed to be 1/5, and the anyonic phase is supposed to be 2 pi times 2/5. So the observed oscillations with large voltage period and weak B field dependent interrupted by discrete jumps is what we see. But in the regions between the discrete jumps, if we're just looking at the evolution of these peaks, you can see that the voltage period here along this stripe is actually 14 millivolts, which is approximately 4 phi naught. This means that it's not just addition. We're still in the incompressible region. We're not just adding quasi-particles in those regions where the AB evolution is taking place. So in the regions between the discrete jumps, the period is 14 millivolts, 4 flux quanta, given that we have a charge for taking into account bulk edge coupling of 1/4. But then we're going to actually look at the bulk edge coupling. The spacing between these the steps is non-uniform as it was before, and that spacing, which is on average about 2.5 phi naught, suggests that this is not just a compressible region where we're constantly adding anyons. So if you go through this analysis, we can actually do it looking at both diagonal cuts and vertical cuts. You can see the difference. And so the vertical cuts show non-sinusoidal behavior due to the unevenness of the quasi-particle addition. The transitions occur because of localized disorder, so you're not going to get periodicity in the vertical direction. But the diagonal lines show sinusoidal oscillations since the quasi-particle number is fixed along these lines, and only AB phase evolution is seen. And so the contours of constant quasi-particle number have a slope that's 0.75 millivolts per millitesla. And that's very close to the value. Remember, I did the analysis at 1/3 for that slope that you would expect given the parameters of our device. Basically, the change in the partial derivative, the change associated with the gate voltage for change in magnetic field can be written down here. Sorry, it's hard to see, but just like we did at 1/3, and the slope is very close to 0.6 millivolts per millitesla, which is very much what we'd expect from the coupling constants we derive from all that analysis of differential conductance. Okay, so if we look at the analysis of the discrete jumps for the inner modes, what can we say? Well, the discrete jumps have different values, but they're also clustered around the value of half times 2 pi. Now, of course, we're not looking for half, we're looking for something closer to 0.4. So the theoretical value for removing an E/5 quasi-particle would be delta theta equals minus the anyonic phase equals 2 pi, times 2/5. But that gets modified because it's bulk edge coupling. Okay, so what we actually see is about 0.54. When we account for bulk edge coupling using the same analysis I did previously, what we actually get is that the anyonic phase is related to the real change in phase slips minus that time plus 3/5 kappa, where, what do we have to change it? Yeah, kappa, again, is this ratio of coupling. KIL is just redefined to K1. This is another paper, so it's a slightly different term issues. It's the same definition. We're just using kappa to stand for the ratio of KIL to KI. And if you do that, what you get is minus 0.43 times 2 pi. The exact answer, unadulterated by any bulk edge coupling or mixing of edge modes, is 0.4. So we also can analyze the charge. The charge comes out at 0.17, close to 0.2. So we did this measurement. It's a much more difficult one. The reason being is because you have a localized charge, you have an interfering charge on the edge that can be either 1/5 or 1/3. You have a very small change in delta nu between the inner state and the outer state. And this small number, delta nu, actually enhances the impact of this bulk edge coupling. The fact that it's so small means that it is a very dominant term. You know, it makes it look like this, but we can still do the analysis. Having done that, we extract the charge of E/5 and the statistical phase angle, as you can see, of 0.43 times 2 pi, very close to 0.4 times 2 pi. So I'm going to wrap it up here. I just got the sign. So conclusions and outlook. I hope for the students, and there's hope. Kun Yang was saying, "Oh, it's all over. There's all the Nobel Prizes have been given. It's done." Well, I'll be here and say there's still stuff to do, and it's not done. And there's lots of exciting things, both in terms of geometric effects, but also in complex experiments, but that can be understood in a system, 2-DEC system like gallium arsenide, because we perfected many control knobs that are still being worked out for other material systems. Okay, so the novel heterostructure design devices overcome challenges in quantum Hall interferometry. It took a long time. The original statement of anyonic phases was 1984. It's 2023 now. But charging effects can be mitigated and sharp confinement potential produced with these in situ screening wells. Clearly defined transitions between compressible and incompressible regimes are possible. And we've been able to quantitatively extract statistical phase and fractional charge at 1/3. And as I hope in the last part I was able to show you, we can also extend this to more complex multi-edge fractions. 2/5 are not only possible to see the effects in some vague way, but to be quantitative about it. And this bodes well for the future experiments at even more exotic states, say 5/2, for example. So with that, I'll conclude, and thank you for your attention.
Questions? So I have one question. question. So for the 2/5, could you explain more about why does it look like 1/3 in your first experiment?
What?
It's your question.
Well, I'll answer it, then maybe you can.
I spoke in just.
Oh, yeah. So the reason is that outer edge mode is, the properties of that are essentially of the 1/3 edge. You know, if you look, you have a region, if you look at what the confinement potential actually does, it goes from a compressible to incompressible to compressible region until you get to zero filling factor. So that edge state is essentially a little strip of 1/3 filling. And so its properties are essentially that of a 1/3 state. Now, the interference, of course, is modified by the presence that the inner droplet is not at 1/3. The quasiparticles there are E/5. And there's this little intermediate strip in between. So the interference signal you'll see and the phase jumps you'll see are modified by the presence of a different type of anion in the central puddle. But the overall shape is still dictated by, you have a 1/3 edge circulating around essentially an incompressible insulating bulk. The fact that the bulk is at 2/5 has some higher order impact on the interference that I didn't get into, but overall, it's just an incompressible bulk. And you see mostly AB evolution. It's as simple as that. Now, if you want to get into what the actual phase looks look like, that is important and subtle. And what's often mistaken in the literature, especially by experimentalists, they'll say it's the 1/3 edge when they have the 2/5 in the middle. It's not really that. It looks close to that, but it's not, you know, there are differences between having a bulk that's at 2/5 and an edge that's 1/3 and having a bulk that's at 1/3 and a 1/3 edge. So, but it's a abuse of language mostly in the literature.
I've also missed, but did you see those jumps in 2/5, which signify a jump which equal to anyonic phase?
Yeah, that's the analysis at the end that we did. Those,
So
the jumps are big.
yeah,
They're not, they're actually, they sort of dominate your eye when you first look at it.
maybe can you go back to like,
So, you know, if you're going from here
so it's basically from
across those.
I see those.
Yeah. You have to look one way when you're looking, and then you look the other, sort of the other way when you're trying to say where the big facelift is.
I see. Right, so they're much larger than.
Yeah, and they're much larger than 1/3, and the AB evolution in between is much reduced.
Okay.
For understandable, I think, reasons.
The questions?
I guess you meant to say 2/3 at the end, not 2/5.
Did I say? No, I mean 2/5.
You
What did I say?
You said in the outline, you said about 2/5.
We did 2/5,
Yes.
and now what I hope to do is this one. We've already done 2/3.
Yes.
The analysis of all that interference is not complete yet, so that's not published. What we have published on 2/3 is the conductance plots of the QPCs, where we see quantization at not only the full 2/3, but at half E²/H. And there's, well, Kunyang has worked on this as well. But that data is also, if you do the Landauer-Boudicca formulas, is consistent with the original proposal, you know, of the imposed whole state on top of the nu=1 state, and you have a counter-propagating charge mode of 1/3. And
But
so
now this is predicated on the assumption that the nu= region is relatively wide, so that you can distinguish that,
yes,
and that there is no reconstruction.
absolutely. And that's not what's been seen historically.
Right.
And the reason is
exactly the same reason our interference experiments work now and not before, because the vast majority of all edge states studied in gallium arsenide fractional quantum Hall physics have soft confining potential and are very susceptible to reconstruction. A point maybe I should have emphasized more is that the screening wells not only reduce the charging effects, but they produce a more sharp confining potential. You can do the numerics on it. We see these very abrupt steps in conductance, and that's indicative of having a sharp confining potential. And the only way you get this downward stream nu equals 1 charge mode and upward stream 1/3 hole mode is if you have sharp edges. And so that's another, that is not what's been seen before. So in the step of doing interference at 2/3, we just looked at it and said, hey, look, there's quantization at 1/2. And that's, again, you have to go through a little bit of the Landauer-Budeker formalism, but that's consistent of 1 downstream and minus 1/3 upstream.
Other questions? If not, let's thank the speaker again.
Thanks, guys.
And that's all for today's lectures.
Kunyang, did you check Amazon? Did you get any more orders on Amazon?
It's not that quick.
My rate is based on how many clicks he gets. So
But what would be really helpful is going to write a review again.
Signed Kunyang's friend.